The James Webb Space Telescope was not supposed to do this. It was built to look backward in time, to catch the faint glow of the first galaxies, to read the atmospheres of alien worlds light years away. It was never designed to stare at something in our own backyard and come back with results that made scientists uncomfortable. But in January 2025, Webb did exactly that. It turned its infrared eye toward one of the most overlooked planets in our solar system, and for 15 straight hours, it watched. The planet was Uranus, and what Webb found there is genuinely unsettling. The results, published in February 2026, revealed a three-dimensional map of Uranus's ionosphere, a ghostly layer stretching thousands of kilometers above the cloud tops, where the atmosphere becomes electrically charged and tangles with one of the most chaotic magnetic fields in the entire solar system. The data showed patterns that models never predicted, vertical structures that don't behave the way they should, and a planet that has been quietly cooling for over 3 decades with no clear explanation why. This is the part of Uranus that no one talks about. Not the tilt, not the moons. The invisible shell of charged particles that wraps around the planet and interacts with space itself. And Webb just ripped it open for us to see. To understand why this matters, you first need to understand what makes Uranus so fundamentally strange. Every planet in our solar system has a magnetic field. Earth's is relatively tidy, aligned more or less with its spin axis, which is why compass needles point north. Jupiter's is enormous and terrifying. Saturn's is almost perfectly symmetrical. But Uranus breaks the pattern entirely. Its magnetic field is tilted nearly 60 degrees away from its rotation axis, and it doesn't even pass through the center of the planet. It's offset, shoved to one side, as if someone knocked it loose. And remember, this is a planet that is already tilted 98 degrees on its side. So what you end up with is a magnetic field that wobbles, sweeps, and tumbles through space in a way that no other planet in the solar system can match. It's not just unusual, it's the strangest magnetosphere we've ever encountered. Now, sitting at the boundary between that wild magnetic field and the upper reaches of the atmosphere is the ionosphere. Think of it as the planet's electrical skin. It's the region where sunlight and charged particles from the solar wind strip electrons from gas molecules, creating a soup of ions and free electrons. On Earth, this layer is responsible for bouncing radio signals around the globe. On Jupiter, it fuels some of the most spectacular auroras in the solar system. On Uranus, until now, it was almost entirely a mystery. We knew it existed. We could detect faint traces of a molecule called H3+, a type of ionized hydrogen that glows in infrared when it's energized. But we had never been able to map it vertically, layer by layer, across the entire planet. We were working with a single blurry snapshot from Voyager 2 in 1986, and a handful of ground-based detections made from telescopes on Earth, squinting through our own atmosphere. That changed on January 19, 2025. A team led by Paola Tiranti at Northumbria University in the United Kingdom pointed Webb's near-infrared spectrograph, called NIRSpec, directly at Uranus. They used its integral field unit, which doesn't just take a picture, it breaks the light apart, wavelength by wavelength, across a 2-dimensional field. That means for every point across the face of the planet, they could measure the temperature and density of ions at different altitudes, building a vertical profile of the atmosphere for the first time. And they watched as Uranus slowly turned, capturing data from nearly every longitude. It's believed to be the only dataset in existence that has continuously observed a full rotation of Uranus from a single telescope. What they found was both beautiful and deeply puzzling. First, the temperatures. The ionosphere of Uranus is not uniform. It peaks between 3,000 and 4,000 kilometers above the cloud tops. That's not at the very top. That's in the middle of the ionosphere, which extends even higher. The average temperature they measured was around 426 kelvins, which is roughly 150 degrees Celsius. Now, that might sound hot, but here's the thing. It's colder than expected. Much colder than what ground-based telescopes had measured in previous decades, and significantly lower than what Voyager 2 inferred during its brief flyby in 1986. And this isn't a random fluctuation. It extends a cooling trend that scientists first noticed in the early 1990s. For over 30 years, the upper atmosphere of Uranus has been steadily losing heat, and nobody can fully explain why. Think about that for a moment. This is a planet nearly 3 billion kilometers from the Sun, receiving about 400 times less sunlight than Earth. It shouldn't have much heat to lose in the first place, and yet, its upper atmosphere has been quietly bleeding warmth into space for 3 decades. Where was the heat coming from originally? Where is it going now? What turned off the tap? These are questions that Webb has sharpened, but not answered. And the deeper you go beneath that cooling ionosphere, the stranger Uranus becomes. The word ice giant makes it sound like a frozen snowball. It's not. Below the cloud tops is a churning fluid of water, methane, and ammonia, compressed under pressures so extreme that the molecules themselves are crushed and rearranged. Scientists believe that deep inside Uranus, the pressure squeezes carbon atoms out of methane and forces them into crystalline structures. In other words, it rains diamonds. Millions of carats falling slowly through a dark, superheated ocean that no probe has ever reached. If you could somehow descend through the upper atmosphere before the pressure killed you, you wouldn't see blue skies. You'd smell rotten eggs. The upper clouds are laced with hydrogen sulfide, and the temperature at the tropopause plunges to minus 224 degrees Celsius, making Uranus the coldest planetary atmosphere in the entire solar system. Colder than Neptune. Colder than anything else orbiting our sun. For decades, this extreme cold was its own mystery. Voyager 2 measured so little internal heat radiating from Uranus that scientists assumed the planet was essentially dead inside. A frozen core left over from whatever cataclysm knocked it on its side. But recent studies in 2025, using computer models and decades of spacecraft data, have challenged that assumption. It turns out Uranus does radiate slightly more heat than it absorbs from the Sun. Roughly 12.5% more. It's not much compared to Jupiter or Neptune, but it's not zero. The planet isn't dead, it's just whispering. And that whisper is getting quieter every year, at least in the upper atmosphere. Which brings us back to what Webb found above those clouds. Then came the auroras. Webb detected 2 bright bands of infrared emission near the magnetic poles of Uranus. These are its auroras, similar in principle to the northern and southern lights on Earth, but shaped by a magnetic field so twisted that the auroras don't sit neatly at the poles. They sweep and shift as the planet rotates, painting glowing arcs across the atmosphere in patterns that change with time. The 2 bright bands Webb detected lined up with what scientists expected from the magnetic field geometry. But between them, something else appeared, a dark region, a gap where the emission dropped sharply and the density of ions fell away. Fewer charged particles, less infrared glow, almost like a shadow cast by the magnetic field itself. This kind of feature has been seen before, but only at Jupiter, where the magnetic field creates defined lanes that guide charged particles through the upper atmosphere. In some regions, the field lines arc outward into space and carry particles away, leaving dark corridors in the aurora. The fact that a similar feature exists at Uranus tells scientists something important. Despite its chaotic, tilted magnetic field, there is structure here. There are rules being followed. The magnetic geometry is carving the ionosphere into distinct zones, funneling energy into some areas and starving others. It's not random, it's patterned. And those patterns change as the planet rotates. Because the magnetic field doesn't rotate in sync with the atmosphere. It precesses, wobbles, like a spinning top that's been kicked. This is where the discovery becomes more than just a data point about one ice giant. Uranus is one of only 2 ice giant planets in our solar system, the other being Neptune. And ice giants are among the most common types of planets found orbiting other stars. When astronomers discover an exoplanet 2 to 4 times the size of Earth, there's a good chance it resembles something like Uranus or Neptune, far more than it resembles Jupiter or Saturn. Understanding how energy moves through Uranus's atmosphere, how its magnetic field shapes its ionosphere, how its auroras form and fade, this isn't just about one overlooked planet, it's a template. A reference point for thousands of worlds we can't visit, but desperately want to understand. And that reference point just got a lot more detailed, because Webb didn't just confirm what we already suspected, it challenged some of our models. The ion densities Webb measured, for example, peaked around 1,000 kilometers above the cloud tops, lower than where the temperatures peaked. That vertical separation, ions concentrated lower down, temperatures highest further up, doesn't perfectly match what one-dimensional models of the ionosphere had predicted. The densities were also lower than those models expected, which means either the models are oversimplified or there are processes happening in the ionosphere that we haven't accounted for. Energy being deposited from above by the solar wind. Heat being transported laterally by atmospheric winds. Chemical reactions destroying ions faster than predicted. The data is pointing in directions the models haven't explored yet. And here's something else that adds to the mystery. Just weeks before this Webb study was published, another team announced that they had finally solved a 39-year-old puzzle about Uranus's radiation belts. When Voyager 2 flew past in January 1986, it detected electron radiation far more intense than anyone predicted. For decades, scientists assumed Uranus simply had strangely powerful radiation belts. But a team from the Southwest Research Institute went back to the Voyager data and compared it to space weather events observed near Earth. Their conclusion was that Voyager 2 had caught Uranus during a rare solar windstorm, a co-rotating interaction region that temporarily supercharged the planet's radiation belts. In other words, we didn't see Uranus as it normally is. We saw it during a cosmic tantrum. That realization changes everything about how we interpret the only close-up data we've ever had from this planet. It means our baseline understanding of Uranus's magnetic environment has been built on a snapshot taken during an exceptional event. And it makes Webb's new observations even more valuable, because Webb is seeing Uranus under what appear to be relatively normal conditions. No flyby, no single pass. 15 hours of steady, patient watching. This is closer to the real Uranus than anything we've ever measured. Still, Webb can only see so much from 2.8 billion kilometers away. It can map the ionosphere, it can trace the auroras, it can measure cooling trends and detect dark zones between auroral bands. But it can't tell us what's happening deep inside the planet. It can't taste the clouds. It can't fly through the magnetic field and measure it from the inside. For that, we need something else entirely. And that something is coming. NASA and the broader planetary science community have identified a Uranus orbiter and probe as the highest priority flagship mission for this decade. The plan, if it moves forward, would send a spacecraft to orbit Uranus and drop a probe into its atmosphere. Not a flyby lasting a few hours like Voyager 2, but an extended mission lasting years, circling the planet, measuring its magnetic field from every angle, and watching how that field changes as Uranus tumbles through its orbit. An orbiter could do what Webb never can. It could fly through the magnetosphere, sampling charged particles directly, measuring the electric and magnetic fields in real time as the planet rotates beneath it. It could watch the auroras shift and evolve over weeks and months instead of a single 15-hour window. And the probe, if it survives long enough during its descent, could taste the atmosphere, measuring the exact ratios of hydrogen, helium, methane, and heavier elements that would tell us where Uranus formed and whether it migrated from somewhere else in the early solar system. Then there are the moons. Uranus has 28 known moons, and the strangest of them all is Miranda. Voyager 2 caught only a brief glimpse of it, but what it saw looked like a world that had been shattered by a collision and then clumsily reassembled by its own gravity. Mismatched terrains slam together, canyons deeper than the Grand Canyon, and a cliff called Verona Rupes that stretches 20 kilometers high, more than double the height of Mount Everest. An orbiter could tell us whether Miranda's scars are truly from a catastrophic breakup or from some other geological process we haven't considered. The earliest such a mission could arrive is likely the 2040s. Until then, Uranus will keep drifting through the outer solar system, rolling on its side, dragging its broken magnetic field behind it, its ionosphere slowly cooling for reasons we don't understand. Webb has given us the clearest portrait yet of this planet's invisible upper atmosphere. It has shown us auroras sweeping across a world shaped by magnetic violence. It has revealed vertical structures that don't match our predictions. And it has confirmed that even the quietest-looking planet in the solar system is anything but quiet. We've spent decades treating Uranus as the boring one, the featureless marble, the afterthought between Saturn and Neptune. But every time we actually look closely, it turns out to be one of the most complex and confounding worlds we know. A planet knocked sideways by ancient violence, wrapped in a magnetic field that defies every model, hiding an atmosphere that has been silently bleeding heat for over 30 years. And now, thanks to Webb, showing us auroras that trace invisible forces we've barely begun to understand. We are not looking at a simple world. We are looking at a puzzle that keeps getting bigger the more pieces we find. And the most important piece, the one that could tie it all together, is still out there, waiting for us to send a spacecraft brave enough to go and get it. Thanks for watching, and I'll see you in the next one.